Hey guys, so in this video I have a few questions that I'm going to discuss. So these questions are based on the concepts that we have discussed earlier, that is contrast random variables, joint probability distributions, right? So I have a set of 10 questions and I'm going to try to discuss all of them in this video only. And if I'm not able to discuss all of the questions, then I'll make another video for this, right? So let's get started. The first question says that a random number x uniformly distributed on 0 to 1 divides 0 to 1 into two segments of lengths x and 1 minus x. Let r be the ratio of the smaller to the larger segment, where r is given to us as ratio of smaller divided by the larger segment. So the smaller segment will come in the numerator and the larger segment will come in the denominator. Hmm. I hope this is better. Right, so they have given us two forms, right? And they have told us that x is uniformly distributed on 0 to 1, 0 to 1, right? So now if I divide any line segment in two parts, where the first part is x. So for example, x lies anywhere on this line 0 to 1. So if x lies here, so if x lies here hmm, so if x lies here, then this segment is x, and this segment would be 1 minus x, right? So now for example, x lies here and this is 0 to 1, so this whole segment would be x and this segment would be 1 minus x, right? And what if x lies here, this segment would be x and this segment would be 1 minus x, right? So when will x be greater than 1 minus x? X would be greater than 1 minus x, that is the larger segment would be x, when this is the first case, when x is the larger segment. So this would happen when 2x is greater than 1, that is x is greater than half. So whenever x is greater than half, our larger segment would be x, smaller would be 1 minus x, right? And whenever x is less than 1 minus x, then this would happen for x being less than half. So whenever x is less than half, our larger segment is 1 minus x. Our smaller segment would be x, right? Now they have given us two cases. Let r be the ratio of the smaller to the larger segment. So r is given to us as this, r is given to us as this, or r is given to us as this, depending on whether x is less than equal to half or x is greater than half. Now they have defined r as r is the ratio of the smaller segment to the larger segment. Smaller segment to the larger segment. Now they have asked us what is the distribution of what is the distribution of R? They asked us the distribution of R, right? So what is the distribution function? So if the distribution function is f of R, then this means that probability of R less than equal to R, right? Right? This is the distribution function, right? So now let's just calculate the distribution function. But first, let me define R. Let me define R, because R can be x upon 1 minus x, or it can be 1 minus x upon x, depending on whether x is greater than 1 minus x or x is less than 1 minus x, right? So R is basically x upon 1 minus x, that is x is the smaller segment when x is less than equal to half. I'm including half here, right? So the larger segment is 1 minus x, the smaller segment is x. So when this case is there, x would be less than half, less than equal to half. I'm including half. I need to include half in either of the two intervals, and they have already told me that x is included in this interval, right? So x is so R is x upon 1 minus x, and the second term for R can be 1 minus x upon x, and this will happen when x is greater than half. So this case, right? So we know what is R. Now we just need to calculate the distribution function. Right? So f of R. So for f of R, now I've already explained this. Wait a minute. Let me zoom this out. So I've already explained this earlier. Just give me a second. So I've already explained this earlier. How do we find the distribution function in a case of transformation of a random variable, right? So I've already explained these kinds of questions in my previous videos. So essentially what we're doing is we need to find probability of r less than equal to r. This means that we need to find the probability of x upon 1 minus x less than equal to r plus the probability of 1 minus x upon x less than equal to r, because two cases are given to us, right? In the first case, r is equal to x upon 1 minus x, where x is less than equal to half, and in the second case, r can be 1 minus x upon x when x is greater than half, right? So I have this term given to me and I have this term given to me, but they haven't really told us about r, or what is the distribution of r, but we know the distribution of x. We don't know the distribution of capital R, right? We don't know the distribution of x upon 1 minus x or of 1 minus x upon x, but we know the distribution of x. So we'll use that. We'll convert the whole function into a function of x only, and then we'll use that function to calculate the distribution function. So what I'll be doing is I'll try to convert this whole term and this whole term in x. So I'll take x to the one side, to any of the sides like the LHS or the RHS, right? And also note that x belongs to 0 to 1. X belongs to 0 to 1. That means that x is positive, and that also means that 1 minus x is positive or equal to 0, right? So whenever the two terms x and 1 minus x are both are positive greater than equal to 0, then we can essentially take them to both of the sides without changing the inequality sign, right? That's why I wrote this again. So x upon 1 minus x less than equal to r, this gives me x less than equal to r minus rx, and this becomes probability of 1 minus x less than equal to rx. This gives me rx plus x less than equal to r, and this gives me 1 Rx plus X. Now this gives me R plus 1 less than equal to R, and this gives me probability of 1 less than equal to R plus 1 into X. So this becomes probability of X less than equal to R upon R plus 1, and the probability of 1 upon R plus 1 X being greater than equal to 1 upon R plus 1, right? So now let me just calculate this. Now see, we already know about X, right? Now I just need to integrate the function. So the lower limit for X was 0, and the upper limit for X is given to us as R upon R plus 1. So 0 to R upon R plus 1 and 1 dx, simple integration in a uniform distribution. I've already discussed this in the previous videos, so go and check them out. And adding it, this would give me, now the lower limit would be 1 upon R plus 1, 1 upon R plus 1, and the upper limit would be 1. Dx again, 1 into dx. This would give me R upon R plus 1 minus 0 plus 1 minus 1 upon R plus 1, right? And this gives me R plus 1 minus 1 upon 1 plus R, and 1 gets cancelled. Finally, what I've gotten is f of R, which is probability of R less than equal to R, is equal to 2R upon 1 plus R. This is my final term. Right? So this was what we need to find. So this question is done now, right? Now let's discuss this question, right? This is an important question. This is a tough question. What has happened? I don't know. Just go on to a new page. So this question says that consider independently and identically distributed random variables x1, x2 till xn with values in 0 to 2. Each of these random variables is uniformly distributed on 0 to 2. If y is max of x1 till xn, the mean of y is, we need to find the mean of y. So this is pretty easy. I've already discussed this earlier, but I'm going to solve the question from scratch. Now let's see what we need to do. So we need to find, again, this is like the previous question only. We have to again find the transformation of random variable, but the process is going to be different. Like the basic process is the same, right? There are going to be some changes which you'll be able to figure out when I'm solving it, but uh, the basic idea is the same, right? So the basic idea is that y is the max of x1, x2 till x3 till xn, right? And this, they are independently and identically distributed. So x1, x2 till xn are IID random variables, independently and identically distributed IID random variables, right? Now we need to find the mean of y. Now for finding the mean of y, I don't have the PDF of y. The formula for any variable, the formula for any random variable, say x is the random variable, or say u is the random variable here, right? So let u be any random variable, and the formula for finding the expected value of u would be u into f of u du, right, from minus infinity to infinity, because I'm just taking minus infinity to infinity, right? So let u be defined over minus infinity to infinity, and this would be the formula for expectations, where f of u is the marginal PDF for u, or just the PDF of u, right? I'm saying marginal when we are talking about joint. We say that this is the marginal PDF of u when we're talking about a single variable. But you can just say that this is the PDF for u, right? Let me just remove the board marginal here. So this is just the PDF for u. F of u is the PDF of u, and we know that we already know that we can find CDF, right? So in the previous question we found the CDF. So this is the process of finding the CDF, right? And here also you find the CDF only. Let me show you. There's some problem here. I don't know why. So we were finding the CDF only here, right? The probability of r less than equal to r, right? This is the CDF, and we know that we can find the PDF from the CDF by differentiating the CDF. So we'll be first finding the CDF, and then we'll differentiate it to obtain the PDF, and from the PDF then we'll calculate the expected value, right? So from the CDF, the first step would be to find the CDF, and the second step would be to go from the CDF, differentiate it, and obtain the PDF by differentiating. The third step would be to find the expected value. Expected, wait a minute. Expected value from, not from, using the PDF, right? Now let me just solve this. Now let's obtain the CDF of y first. So y is max of x1, x2 till xn, and we know that all xi's are identically and independently distributed, right? Identically and independently, so they are identical, right? And all xi is uniformly distributed from 0 to 2. It's given to us, where I is equal to 1, 2 till n, right? Are independently and identically distributed random variables in 0 to 2, uniformly distributed on 0 to 2, right? Now we need to find the CDF of y first. So f of y is probability of y less than equal to y. This gives me probability of max of x1, x2. See, I've already discussed this problem, this exact problem, like not this question, but the whole idea of finding the CDF of the max function. I've discussed this in the previous video, so go and check that out. So the CDF we are trying to find. So the max of x1, x2 till xn less than equal to y, right? Now our whole point is to convert this into a question for x, because we already know the distribution of x, so it will be easier for us. So the max of x1, x2 to xn, and this is less than equal to y. This means that y would be greater than or equal to all of x. So y would be greater than x1 also, and y would be greater than x2 also. Intersection y would be greater than x3 also, and so on and so forth till xn also, right? Because they are independent and identical. Because they are independent, I can write the joint PDF as the product of individual probabilities, right? So we already know that the probability of A intersection B becomes probability of A into probability of B when A and B are independent, right? Also let me just write this property here. fx of y, which is a joint PDF, let fx y be a joint PDF, can be written as the product of the marginal PDFs of x and y each when x and y are independent, right? Now we know that the max of x1 x2 till xn is less than equal to y. This means that the individual values would also be less than equal to y, right? Now we can separate this, right? So this would give me probability of x1 less than equal to y into probability of x2 less than equal to y, and so on and so forth till probability of xn less than equal to y. This means that we can just write this, we can just calculate this, right? Because we know that all xi's are independent and identically distributed, and the distribution that they are using is uniform from 0 to 2, right? So this now 0 to y, so the lower limit is 0 and the upper limit is y, dy, and I'll be using, wait a minute, not dy, dx, dx1 actually, dx1, and this would be half, right? Because the PDF of any uniformly distributed random variable is 1 upon b minus a, where b is the highest value of the integral and a is the lowest value, right? So if my interval was 1 to 2, then it would have been 2 minus 1, which would be 1 upon 1. Had it been 1 upon 7, had it been 1 to 7, uniformly distributed from, had it been uniformly distributed from 10 to 35, right? Then it would have been 1 upon b minus a, 35 minus 10 is 25, right? So 1 upon 25. This would have been the PDF. Now let me just rub this off. So then, so now this gives me this, and in product with this 0 to y again, half dx2, and so on and so forth till 0 to y, half dxn, right? So now this gives me half of y, till n, right? So these are n terms. This would give me half into y to the power n, right? This is my f of y. Now I need to obtain the CDF, right? For obtaining the CDF, I would just differentiate this whole function. This would give me f of y as n by 2 y n by 2 to the power n. So n by 2 to the power n, y would be n minus 1, right? Where y also lies between 0 and 2. Now why does y lie between 0 and 2? Because y was greater than or equal to the max of value, max of all of these values, and the max value can be 2. But remember, the max value can be 2, but the max value can also be 0. What if all of the random variables, because essentially it is a random variable, right? Now the question can arise in your mind that because the max of all of the because the max value that x can attain is 2, then why isn't y essentially greater than or equal to 2? This question can arise. But then ask yourself, all of the x's are random variables. They are distributed from 0 to 2. But we don't know if they are 2 only, if they are 0 only. It might be possible that when we observe those values, all of the values turn out to be equal to 0. Then can you say that y is greater than equal to 2? No. Then y would be equal to 0 only. If all of the values say, if all of the x's are equal to 0, so 0, 0, 0, 0, 0, 0, 0, and this is max of all of the zeros, and y is greater than all of the zeros, then can you say that y is greater than equal to 2? Like it is greater than equal to 2, but then y turns out to be equal to 0 also using this case, right? Hmm. Hmm. Now we have the CDF. Now we need to find the expected value. So finding the expected value of y would be 0 to 2, 0 to 2 y into n upon 2 to the power n upon 2 to the power n, y to the power n minus 1 dy, right? Because this was the PDF. So expected value of y turns out to be equal to so expected value of y turns out to be equal to, now 2 to the power n and n both are constant, so I'll just take that out. 0 to 2 y to the power n d of y. This gives me 1 upon 2 to the power n into n y n plus 1 upon n plus 1 from 0 to 2. This gives me 2 to the power n plus 1 divided by n plus 1 minus 0, right? So this gives me, now 2 to the power n plus 1 and 2 to the power n gets cancelled. This gives me 2. So this comes out to be 2n upon n plus 1. 2n upon n plus 1, right? Let me just see and check if we can match our answer. So 2n upon n plus 1. Now let us solve the third question. Now let's solve this question. Suppose y is a random variable with uniform distribution on 0 to 2. The value of the cumulative distribution function of the random variable x, the CDF of x, equals to e to the power y at x belongs to 1 to e square is, y is a random variable uniformly distributed on 0 to 2. Again, this is a question of transformation of a single random variable, right? It's been long since I've made a video. That's why I'm having trouble in setting the size of the screen, the configuration, right? So let's start with the question now. Y is uniformly distributed from 0 to 2. The value of the cumulative distribution function of the random variable x is equal to e to the power y at x belongs to 1 to e square is. So we need to find the CDF. It's a pretty easy question. So we need to find f of x, which is the probability of x less than equal to x, the probability of e to the power y less than equal to x, which becomes, now I need to take log on both the sides. If I take log on both the sides, I'll be left with log e to the power y would give me y, and this would be log of x. So this would be y less than equal to log of x. So y less than equal to log of x means that, and y is uniformly distributed from 0 to 2. So this would give me 0 to log of x. Now the PDF for y would be 1 upon 2 because b is 2 and a is 0. 0 to 2. Y is uniformly distributed from 0 to 2. This means that b is equal to 2, a is equal to 0. So 1 upon b minus a becomes the PDF of y. 1 upon b minus a becomes 1 upon 2, right? 1 upon 2 dy, which gives me y upon 2 0 to log of x, which gives me log x upon 2, right? Log x upon 2. This is the first option only, right? Log x upon 2. So now let's solve the next question. This is a pretty easy question. So now let's solve the next question. This is the last question that I'm taking this today in this video. Otherwise, the video will be around 40 to 45 minutes long, and I don't want that to happen right now. Otherwise, you guys don't watch the video. Let's solve. Let's solve this question. So this question says that. Two independent random variables x and y are uniformly distributed in the interval 0 to 1. For a z belongs to 0 to 1, we are told that the probability of z being greater than equal to the max of x comma y is equal to the probability that 1 minus z is greater than equal to min of x comma y. What is the value of z, right? So they're telling us that the probability of the max of x comma y less than equal to z is equal to the probability of min of x comma y less than or equal to 1 minus z, right? Where x comma y are independent random variables and are uniformly distributed between 0 to 1, and that z belongs to 0 to 1, right? We need to find the value of z. So this is a pretty easy question. So we already know this. Let's just solve this first. So let u be max of x comma y, and let v be min of x comma y. We need to find the PDFs of both. So f of u, we need to find the probability of u less than equal to small u, which gives me the probability of max of x comma y being less than equal to z, which gives me the probability of, because they are independent, the probability of x being less than z intersection the value of y being less than equal to z, which gives me the probability of x less than equal to z and y less than equal to z, which gives me now they are uniformly distributed, right? So let me just move on to the next page, right? So f of u which is probability of u less than equal to u. Now this gives me, wait a minute, just assume here it to be z. Not assume, it's given to us, right? So u is less than equal to z. But the procedure is right here also, right? So probability of x being less than equal to z into probability of y being less than equal to z, and both are uniformly distributed from 0 to 1. 0 to 1 d of x, 0 to z, and 0 to z, 1 upon 1 d of y. This gives me z square, right? Z square. So f of u is z square. Now f of v would be the probability of v less than or equal to z, less than or equal to 1 minus z. It's given to us that it is less than or equal to 1 minus z. 1 minus z. So probability of min of x comma y less than or equal to 1 minus z. This, now for this, the min of x comma y is less than or equal to 1 minus z. So this we can't write it in the previous way. Why? Because if x is less than or equal to 1 minus z, then that does not mean that y is also less than or equal to 1 minus z. So for example, between x and y, let's just say that x is less than y. So we can write that the min of x comma y, which is x, is less than or equal to 1 minus z. But it can happen that even if x is, which is the min of x comma y, is less than or equal to 1 minus z, y is greater than or equal to 1 minus z, right? So we can't generalize the term and say that x is less than equal to 1 minus z intersection y is less than equal to 1 minus z and separate them out, then repeat the whole process. This is not possible here, right? But what if I tell you I can write this exact term as 1 minus probability of min of x comma y greater than or equal to 1 minus z. Now, if the min of x comma y is x, so if x is the min of x comma y x, which is x, let's just assume that it is x. So if the min of x comma y, which is x, is greater than or equal to 1 minus z, then that means that y, which is larger than x, would also be automatically greater than 1 minus z, right? So we can use this. So I'll just write this as 1 minus probability of x greater than or equal to 1 minus z intersection y greater than or equal to 1 minus z, which gives me 1 minus probability of x greater than or equal to 1 minus z and y greater than or equal to 1 minus z, which again gives me the probability of 1. Now I can write x greater than or equal to 1 minus z as 1 minus probability of x less than or equal to 1 minus z. Now x and y are both uniformly distributed from 0 to 1. So this would give me x being less than or equal to 1 minus z would give me integrating the PDF of x, which is 1, and same for y as 1, integrating it over 0 to 1 minus z, right? Which would give me again 1 minus z. This would be 1 minus z, and this would again be 1 minus z. 1 minus 1 minus z, right? So this would become 1 and 1 would cancel, and this would be 1 z, and this would also be z. This would give me 1 minus z square, right? Now we know that the probability of max of x comma y less than or equal to, so now this was probability of min of x comma y less than or equal to 1 minus z, right? And this was the probability of, max of x comma y less than or equal to z, which is z square. Now I need to equate both of these terms, right? Is equal to the probability of min of x comma y less than or equal to 1 minus z. This would give me z square and this would give me 1 minus z square. So 2z square is equal to 1. Z square turns out to be half, which implies z is equal to plus minus 1 by root 2. But it is given to us that z belongs to 0 to 1. So we'll reject the value of z being minus 1 upon root 2. So final value would be z is equal to 1 upon root 2. 1 upon root 2. Right? So this is our final value. Let me just see if it matches. Yes. So z is our final value, which is 1 upon root 2, which is option B. So I feel I've discussed around 1, 2, and 3 questions in this video, right? So 3 questions. I guess this is enough for this video. In the next video, I'm going to discuss 3 to 5 questions more, and then I'm going to jump making more videos on distributions and discuss more questions from the book Fundamentals for Mathematical Statistics, the book which I was referring earlier, right? I also showed that video, that book, in one of my videos, right? I guess I'm sleepy right now. It's 4:30, 4:40 a.m. So I'm not able to put my thoughts correctly. But yeah. So bye bye. Like, share, and subscribe the video, and do put in a comment if you like the video. Thanks.